Welcome back to our next presentation. Sorry for the short delay. We had to clarify a few technical issues in the background. So we're ready for the next presentation, which will be given by James Hui. He's a CIMIC Senior Solution Architect for the simulation and agile practices at Wind River. He has 20 years of experience in software development across a wide range of domains, including industrial automation, machine learning, predictive maintenance, avionics, and defense. He's a chartered engineer by the Institution of Engineering and Technology, a certified Scrum Master, and a certified Scrum Professional, what definitely qualifies him for his next talk on Agile test orchestration for embedded software. James, please start.
Thank you very much for your kind introduction. Thank you. Hello, everyone. Good morning, good afternoon, and good evening. Hope you are all doing very well, wherever you are in the world. It is my pleasure to take part in this virtual Embedded World Conference. And my name is James Hui, Solution Architect from Wind River. I'm an engineer, and I have been enjoying my embedded software engineering for the last 25 years. And I live in London, the United Kingdom. My interest is on simulation for testing, as well as model-based design. Today, my short 30 minutes talk is a technical presentation. I like to talk about what we mean by Agile test orchestration and how we can use deterministic simulation to help us to achieve this. Of course, this is just one of the many possible ways of achieving large-scale testing with confidence. And we don't believe that this is the only way, nor this is the best way. Of course, there are many other ways, and there are ways that is still under development or even not exist yet. So all I want to do in the next half an hour is to share our journey, our lessons learned, and hopefully this very short talk will plant a small seed in the near future with you as an engineer to innovate and build more dependable systems. I must say that I enjoyed the earliest Rob's presentation a lot. I agree with him that he points out that tester need to make code, the developer need to make code testable. And also the tester and developer need to work together, and I like it a lot. Last but not least, tests really need to be involved in the design cycle early on, so I can't agree more than that. My perspective, adding on to Rob's, is test actually is our first-class citizens in terms of software development lifecycle. Tests in the Agile context is more than just checking our code, whether it works or not. It gives us insight as an engineer to innovate, to benchmark, and also to improve. This required determinism and also a systematic way to examine, to exercise, to experiment with our code while we're developing this embedded system. So I'm very glad that I can share our viewpoint today, how we think simulation is a key enabler for us to gain feedback from our software, which can be decoupled and operate independently just on a generic PC rather than special hardware. With no special hardware required, we can start prototyping, we can start testing, we can start experimenting without fear. However, I want to be clear, the assumption here is to make not just simulation, but a fast and deterministic simulation, not any simulation. We have learned our lessons, hence we want to share it with you. Let's start with our story from our perspective on the need of running the embedded software tests with simulation, then how a base test infrastructure contains. Finally, we then start to talk about orchestration and improving the test performance. If we have enough time, I would like to play back a live demo so that you can see how a deterministic simulator in action. Feel free to reach out to me if we just simply don't have enough time to cover it today. So for the audience who are not familiar with Rim River, we are a software company specialized in real-time operating systems. Our software is used in many mission-critical applications, such as aerospace, telecommunication, 5G infrastructure, automotive, industrial automation, as well as space. It powers many satellites, space probe, and Mars rover as well, such as Curiosity as well as Perseverance. I've been told that by my colleague that we now have a market domination in the red planet, but just not on Earth yet. So we still need to work very hard on it. This year is a very special year for us because the company is founded in the United States in the last 40 years ago. From day one, developing code that just works is only a small part of our work. A larger piece of our effort actually is dedicated to testing and verification, which keep us busy for many, many years. Very, very roughly speaking, the ratio between our test code and our production code is round about 1,000 to 1. So traditionally, we have been relying entirely on hardware-based testing at the point that we even develop our own board, our debugging adapter to assist our engineer and customer to gain visibility into the embedded software. These components help us to understand how the software component is working with each other and also how it's interacting with the hardware registers. It helps us to find bugs that cause frustration and confusion to the engineer. But very quickly, we learned that our DNA actually is on software, not on hardware. Building hardware is hard for us, and maintaining all the boards, all the debug adapter distract us from doing our own job. And however, we know that work is not done until it's being tested. Our customer paid us to deliver working code, not just code or any code. Working means that it needs to create value for the customer who use it in the future. Hence, checking the code does what it claims on the tin is only the first step. There's a higher layer that we need to obtain insight and also get feedback from how the code performs in terms of safety, security, reliability, so that we can help some of our customers to achieve certification requirement. Continuous testing forces us to exercise our software 24 hours, 7 days a week. It keeps our code base cleaner and more agile, and also improve the ability to accept changes at any time in the development cycle. So on the right-hand side is a picture that we take before our digital transformation. It is one of our labs, and we have many of them around the world. As you can imagine, it is not an easy place to work in. I sometimes worry about a cable have fallen. I worry about the power to my board. I worry about where to put my new board when the next project comes. Well, you can say that I worry a lot, and yet there are things that I didn't expect, like here comes COVID, the pandemic. Most of us now need to work from home and not able to access to our office nor lab now. In order to keep up with the pace of 24/7 continuous testing and also providing insight back to the engineering quickly, we start moving some of these tests away from the real hardware. From the start, we understand that simulation is not a hardware replacement. There are still tests that need to be done and absolutely have to be done with hardware. But there are tests, in particular, functional tests, business logic code, that can nicely lend itself by running on a simulator. So we like to run as many tests as quickly as possible, and only functional level result is needed. More precisely, we are talking about data transaction level, where data is being transferred from one register to another register. Raising the simulation abstraction helps us to improve the simulation performance by a factor of thousands. It is a matter of booting the operating system in 4 hours, comparing with 10 seconds. Since simulation runs on generic PC, there are little overhead on the equipment maintenance. A simulation runs on the same PC that I build the code, or alternatively, the engineer have the option and the freedom to hire a server in minutes and launch the simulation remotely. Running the application software on a simulator, we can pause the simulator at any time. One trick that we have learned is that when the simulation is paused, we can create something called a checkpoint. And this checkpoint is a snapshot of the current state of the simulation so that we can archive it and restore it later. A deterministic simulator is able to restore this kind of simulation so that we can create multiple checkpoints during a simulation run. Then simply we have created time portals that we can jump from one time in the simulation to another time of simulation if we need to track down some difficult bugs. Sometimes some part of the code is really difficult to reach and exercise. So on this basis, we create the code. We want to run this code without modification. And simulation is the tools that help us to stop the software, let us manipulate the memory region, unplug the device, or even corrupt a network package. Sometimes we also insert a faulty sensor model into our simulation to challenge the software in order to exercise every bit of the code base. So there are two key design perspectives when we're developing this base test infrastructure. We like it to be upgradable as well as extendable. Upgrade, we refer that if we have a new version of the model or a new version of the device that we want to simulate, we can just roll it out to the model and let everyone use the tools to choose which version of their software want to use it or replacing an existing one. Extendable, we refer to the platform need to be open for engineers so that they can develop their own model, add it into the simulation to test their code, such as their own FPGA device or any bespoke data bus. On the right-hand side, there's a snapshot of one of our base tests. So in the picture on the left-hand side here, these are all the loosely coupled objects like Lego blocks that builds up the tests. You'll find the objects such as the CPUs here, the memory, and the Mac and the PHY. All these individual components are put together using scripting, and they can all be version controlled individually. Building a test base which is repeatable, relying on the use of scripting. Popular tools, we can use Python, Bash, or a batch file on Windows. This script are recipe that captures the test knowledge. For example, what are the components, the objects, and how they link with each other. Every time the script is called, the same simulation configuration is created. It is only when we have the same simulation configuration, we will be able to have this common baseline of tests. So such as Dr. James Harrington says, you can't improve what you don't measure. Therefore, there are many commercial tools and open source projects help us to build such systems. So on the right-hand side, it's just a typical automated regression test flow that utilizing these tools. Taking this further, we also started to containerize the test simulation. It defines the atomic unit of the test container, which frees our tests from running on a particular generic PC that have the tools installed. The test container itself contains everything that the test require to be executed. The test container is there the common platform for the team to share. if they need to run the same similar kind of tests, it avoids the situation that it works on my PC problem, and it also improves portability. The test container only allocate resources when it's launched, and it automatically tears down and frees up resources when the test script is completed. We can launch multiple copies of the same test container by feeding in different application code and different test binary in order to run tests in parallel to speed up time. Sometimes we can also use the same binary, same test, but different version of the test container to test different test configuration. After we understand that the possibility of running multiple copies of the test container statically, it opens up another door to leverage orchestration technology to dynamically scale testing to match the test demand by the user as well as the resources that is available in your infrastructure. Resource can join and leave the test orchestration cluster, and leveraging popular tools, both open source and commercial tools, help us to integrate such infrastructure. On the right-hand side, we attempt to illustrate a simulation that can be paused at some time to create a checkpoint, and which the simulation archive then is being cloned into to run on multiple nodes using the test container, and they all starting their test based on the same checkpoint. So we are migrating from a locally installed tools to a containerized tools, and looking into the multi-containerized tools with orchestration. So let me try to show you how a concrete example of how this simulation looks like. And in here, I'm trying to simulate on a generic PC a space grade CPU. You can the same technique can be applied on ARM and PowerPC or Intel processor as well. Okay, so let me just skip ahead a little bit so that we can see that it is running on a generic PC with Linux, and I've got 8 core on this machine. And these are our test binary, the operating system code, as well as some script to help me to do the test. And if I examine the code, I can see that the code actually is compiled for this Spark machine, and I've got a Docker container that this is our test container that have got everything inside the container for me to simulate this board. So we can see that this container is just under 1.7 gigabyte. So with the container, then I can start launching the simulation on the command line. I also put down time to measure how long this simulation will take to run. So in here, we can see that very quickly, just under 2 seconds, we're able to, the simulator picks up the binary and then booted the system. So this is what we mean by a fast deterministic simulator can do, is it can pick up the binary, your production binary, and then boot the system in seconds and not hours. And we can see that it is booting our operating system this time as an example, and it can be any other operating system as well. So we can see that the checkpoint is created in this demonstration, and we can then reuse this checkpoint as our test baseline to further do other application tests from then on. So I'm launching the container again, and this time it will now perform the test because it's already found the checkpoint and perform various function to provide me with the text log to inspect later on. So once we have got these tests and test log, we can integrate all these scripts into a Git repo to develop the automated test infrastructure. So we can check in the code, just the same code that we have used earlier in when I'm running the simulation locally, but now I'm moving all these code onto a server repository, and we can also create a Jenkins job which is going to launch the Docker container on demand when it sees changes in the code. And we can see that we are running exactly the same Docker container as we was earlier. So we're reusing the simulation, and we are going to archive the or the simulation result once the build job is finished. So in here I am building and running the tests, and we can see that very quickly on the server it finished running all the tests, booted the system, it performed the test for me, and then all the tests have been successfully completed. And if I go back to the panel, the dashboard, I can see the file have been archived. And since everything is on the server, I can use a browser, put in a new test, and then when Jenkins detects the changes, then it's going to rebuild the system for me. And at the end, I've got a new test cases and a test recording archive in the system. Okay, so hopefully this gives you some idea how what we mean by a fast deterministic simulator, how it's integrate with open source tools to create the automated test flow. And as a summary, this is our journey, and is a part of our continuous improvement. The more that we think we know, the more we realize that we don't know. So there's still a lot for us to learn. Keeping tests agile is we want to make tests small, fast, focused, and easily changeable, and with the possibility to regret and roll back. Currently, 99.3% of our tests don't need the real hardware to perform the test. Hence, it is not a hardware replacement. It takes us 5 years to get to where we are now. So it is a long journey for us. And once the hardware simulation works, then our suggestion is to start looking at test containerization. Once you have got test containerization, try look at test orchestration to run more tests more quickly with and maximize the use of your resources. Test orchestration focus on tests that can be decoupled and from the hardware and also from the people. So so you need to pick your test cases and make your code testable, and so that it can be run on test orchestration infrastructure. And last but not least, I need to echo back, is testing is not an option. It is a business strategy to improve the workflow by making more data-driven decision, so that we can gain insight of the product from the product that we are delivering to our customer. So I would like to thank you everyone for your attention, and hopefully it is useful, and thank you.
Okay, thank you very much, James.
Pleasure, thank you very much.
It was
Thanks for
very
having me.
interesting presentation, and we need a few minutes to shift to the next and final presentation given by Sean Prestridge. And I would like to use the opportunity just to encourage you again to add some questions to our Slido stream, which we will be able to answer after Sean's presentation in half an hour. So I'll be back in a few minutes. Thank you very much.